Hello everyone. In the previous video, we have studied about non-ideal solution showing a positive deviation, and here we will study another one, that is non-ideal solution showing negative deviation. So already we know that in case of ideal solution, the components will obey Raoult's law at all concentrations. So if you consider two different components like A and B, the interaction between solute and solvent and solvent, that will be equal to interaction between solute and solvent molecules. And we have seen that the vapor pressure will be whatever the vapor pressure expected from the Raoult's law. And in case of non-ideal solution showing negative deviation, the important thing here is it does not obey Raoult's law. That is, the vapor pressure of the such solutions will be lesser than the expected from the Raoult's law. So the reason for this is, if you consider two different components present in that solution, if I take A as solute, B as solvent, the interaction between AA or BB, that will be having lesser tendency when compared to interaction between the solute and solvent, that is component A and B. So AB interaction will be more compared to AA or BB interaction. So if that is the case, we can imagine a container containing a solution showing negative deviation. In that case, see here, there are different components A and B, red and blue colored one. So there will be more tendency of intermolecular attraction between A and B, like this. There will be also other molecules, other interaction will be there, but the tendency will be less. Okay, solvent interaction will be also there, solute interaction will be also there, but the molecules will be having more tendency for AB interaction. So if that is the case, what happens? So here we can see that for each component, if I consider red one, that is component A, it may be solute. So the escaping tendency becomes less. Why? Because it is bonded to, or it is having the intermolecular attraction with the solvent. So it should overcome that and escape. So that is difficult. So the vapor pressure of this component A, that becomes less. Similarly, if you take solvent component or component B, it will be also having intermolecular attraction with the component A. So here also it should overcome to escape, overcome that force to escape. So here also the vapor pressure will be less, because escaping tendency for each component, it may be A or it may be B, it is less, because each of the component is having intermolecular bonding with the other component, that it has to overcome and escape. So that is difficult. So for both the components, the vapor pressure will be less. So that is why we say that in case of non-ideal solution showing negative deviation, we get the vapor pressure lesser than the which is expected from the Raoult's law. So if you see a graph related to this non-ideal solutions showing negative deviation, so you can see here, like non-ideal solutions showing positive deviation, we have a graph of vapor pressure along the y-axis and mole fraction along the x-axis, and I have written one of the component mole fraction as x1, another one as x2. From here to here, the mole fraction of the component 1 increases. From here to here, the mole fraction of the component 2 decreases, or I can say from here to here, the mole fraction of the component 2 increases. So we know that according to Raoult's law, as the vapor pressure of the particular component will be directly proportional to the mole fraction. So if I take first component, so as the mole fraction is increased, from here to here the mole fraction is increased. As it is increased, what happens to vapor pressure? Vapor pressure also goes on increasing. Okay, this is the maximum possible vapor pressure for which one? Component 1. So this is expected from Raoult's law. Whatever the black color dotted line is there, that is expected from Raoult's law. Similarly for component 2 also, as the mole fraction of component 2 increases, the vapor should go on increasing, and this is the maximum possible value for the component 2. This is according to Raoult's law, and combining these 2 points we get the total vapor pressure of the solution, which is represented by a dotted line which is in black. But in case of non-ideal solution showing negative deviation, what happens? We can see a red colored line below the dotted line. So what does it mean? The red colored lines show that the solution is showing negative deviation from the Raoult's law. So you can see here, for example, for component 1, at the mole fraction, let me take x1 is equal to 0.2 here. At this point, the expected vapor pressure is this one. But if you see the point on this curve, it will show the vapor pressure here. So the vapor pressure has become less in case of such type of solution. So you will get the vapor pressure lesser than the expected from the Raoult's law. Similarly, you can here take component 2. Let me take x2 is equal to 0.2 here, maybe here. So at this point, according to Raoult's law, you have to get the vapor pressure for that component 2 here. But if you see this line, you will get the vapor pressure here. What does it tell? The vapor pressure has decreased. So total vapor pressure, if you see the curve here also, if you expect at this point, maybe you should get some value, but it will be lower than the expected from the vapor pressure of the solution, that is from the Raoult's law. The example for solution showing a negative deviation is phenol and aniline. So in phenol, there is intramolecular hydrogen bonding. In aniline also there is intramolecular hydrogen bonding. But the intermolecular hydrogen bonding between phenol and aniline will be more. So if you see, if you take phenol, there will be intermolecular hydrogen bonding between the lone pair of nitrogen of the aniline and the hydrogen of the phenol. So this, that is AB interaction, will be dominant when compared to AA or BB interaction. Okay, so that's why this phenol and aniline mixture, they show negative deviation from Raoult's law. And also another example is chloroform and acetone. This mixture also show negative deviation from Raoult's law. So here also there will be hydrogen bonding between the hydrogen of the chloroform and the acetone of the oxygen of the acetone. So if this is acetone, it has oxygen, there will be hydrogen, intermolecular hydrogen bonding between the oxygen of acetone and hydrogen of the chloroform, like this. So this AB interaction, that will be dominant when compared to AA or BB. That is, there will be interaction between each components separately with themselves, but also there will be dominant interaction between A and B. So that's about example for non-ideal solution showing negative deviation. This concludes the non-ideal solution showing negative deviation. In the next video, we will study about azeotropes. Thank you.